Okay, so chapter 15, 15A and 15B in specialist maths. These two bits used to be in mathematical methods prior to 2016. And when the course got changed, it got removed out of mathematical methods and got moved into specialist maths. So you might find some examples of probability questions that are really, really old that refer to this sort of work. And there's actually a chapter in the textbook still with an asterisk saying that this is no longer part of the course. What we're talking about are linear combinations of random variables. So for example, I might be considering how much homework I do, and my homework might be the amount of methods homework plus the amount of specialist homework plus the amount of other homework. And there are three things added together as a linear combination. I might do 4 hours of methods, and I might do 6 hours of specialist, and I might do 1 hour from every other subject, which gives me a total of 11 hours. And we're considering each of them which have a separate distribution, but then adding them together to give you a new combination. So it's called a linear function, where we are adding the three separate variables together. So in this section we consider random variable y, which is a linear function of another random variable x. In this particular case, y equals ax plus b. In my particular case here, I would have h equals 1 times methods plus 1 times specialist plus 1 times other. So I'm going to think about this random variable, and I'll get an idea of what happens to the mean. And bear with me for a little minute with this example. If I have x, and x is concentrated around 20, and it sort of has a sort of a normal distribution where the spread goes out to around about 23 and out to around about 17, and that there's very little distribution above 23 and there's very little distribution below 17. And then if I was to consider 2x, that is, the values of x doubled, then I would expect the centre of the distribution to be over here at 40, because everything is doubled. But my largest distribution goes up to 46, and my smaller goes down to 34. Can you see that my spread is much, much bigger than it used to be? It's actually 4 times bigger. It's got doubled in this direction, and it got doubled in this direction as in relation to its spread. However, the mean just got moved over 20 units. It got doubled. If I was to consider x to be centred at 10, and that goes up to about 14, and that goes down to around about 6, and I did y equals 3x plus 5, then I would expect that my mean would get multiplied by 3 to get to 30, and then go out to 35. That the mean of the expected value is multiplied by 3, then 5 is added. My 14 would be multiplied by 3 to get 42 plus 5, so 47. And my 6 gets multiplied by 3 is 18, plus 5 is 23. So my spread got multiplied by 3 that way and multiplied by 3 that way, so it's 3 times bigger that way and 3 times bigger that way. And my mean got multiplied by 3 and then 5 was added, but the 5 had no impact on the spread whatsoever. The 3 did. Any questions about this? Are you happy that 3 produces a dilation, but the 5 produces a translation? That is, the 5 just moved everything 5 units to the right. So if my expected value of x is going to be 10, then I'd expect the expected value of y will equal the expected value of 3x plus 5, which will be 3 times the expected value of x plus 5. 3 times 10 plus 5, 35. I triple my expected value, then I plus 5. I triple my largest value, then I plus 5. Whereas the variation of x, of y, will be 3 times whatever the variation of x was. So in other words, 3 squared times the variation of x. And why do you think it's 3 squared? Any suggestions why it might be 3 squared? Yes, very good. So it gets stretched by 3 that way, and it gets stretched by 3 that way. That this 14 is further away from the mean by a factor of 3, and this 6 also ends up further away from the mean by a factor of 3. So we end up with this 3 squared times the variation of x. So if y equals a times x plus b, then I'd expect the expectation of y to be a times the expectation of x plus a value b. The b is a translation, we just add it afterwards. The variation of y will be a squared times the variation of x. And they're the main rules that we need to follow when dealing with a linear combination of variables. And that's exactly what this says and what this says. So if I have, like my example before, the amount of maths homework plus the amount of spec homework, I've actually got the expected value of x plus y, and I can work out the expected value of doing the average of each of them separately, and the variation will be the variation of each of them separately. That's if x and y are independent. That is, they have no connection between each other. And if I have a range of independent events, so I could do the maths homework plus the spec homework plus the English homework plus the biology homework plus the chemistry homework plus the PE homework, depending upon how many subjects you're doing. So you're going to be adding 1, 2, 3, 4, 5, 6 subjects. Then the mean of them would be each of them separately added together, and the variation of them would be the multiplier squared times the variation of them each separately. That's if they were independent events. Very important if they're independent events. Now, I'd probably suggest that homework isn't an independent event because if you did 4 hours on specialist maths, you're not likely to do as much on other subjects because the other subject depends upon how much time is available in the night. So it's probably not a great example.